So the final piece in the puzzle in deriving an expression for the sound speed is the isentropic flow relations. These govern how the thermodynamic state of a gas changes as a flow goes through an isentropic process, and we'll derive these relations in this module. So if you recall, we found that the sound speed squared was equal to dp rho at constant entropy. In order to evaluate this derivative, we need pressure as a function of density for constant entropy. But how can we ensure that the entropy is constant? Well, we can start with an expression for the entropy change and then set this equal to 0. The most fundamental expression for entropy change is the second law of thermodynamics. This tells us that if we have a gas with mass m, entropy S, and temperature T, and we add a small amount of heat, delta Q, then the change in entropy ds is going to be greater than or equal to del Q over T. If we've got a reversible process, the equality holds, so del Q is equal to TdS. At this stage, I just want to note what the difference between the upper and lowercase letters is. Basically, the lowercase letters just indicate a quantity per unit mass. Now, if we want to put the second law in terms of pressure and density, which is what we need to do to take that derivative, we've got to replace del Q with some expression in terms of thermodynamic variables. We can find an expression for del Q from the first law of thermodynamics. This tells us that if we've got a gas, which once again has mass m and internal energy U, we add some small amount of heat del Q and extract some work del W from the gas, for example by allowing it to push up a piston, then the change in internal energy du is equal to del Q minus del W. If we've got what's known as a quasi-static process, then the work del W is just equal to the pressure times the change in volume dV. This is nothing but a rearrangement of work done being equal to force multiplied by the distance it acts over. If we combine this and the second law, we find that the change in internal energy du is equal to TdS minus PdV. So what we need to do is to put this combined first and second law into a form that we can integrate. We're going to start off by switching to quantities per unit mass. So we've got du is equal to TdS minus PdV. We can introduce the enthalpy by noting that the internal energy U is equal to H minus PV. Taking the derivative of this expression, du is equal to dH minus PdV minus VdP. So we've used the chain rule on the last term. If we make this substitution for du, we have dH minus PdV minus VdP is equal to TdS minus PdV. So we've got PdVs on both sides, so let's cancel off those. And also the specific volume V is just equal to 1 over the density. So let's make that substitution. So we now have dH is equal to TdS, taking this term to the other side, plus dP over rho. So this expression was first derived by Gibbs, and it's going to be useful for later derivations in the course, so let's keep track of it. To get this into integrable form, we need to use the equations of state that we discussed in the last module. So if you recall, dH was equal to Cp dt, and this is going to be equal to TdS plus, now 1 on density from the ideal gas law is just RT divided by P, and that's still going to be multiplied by dP. Now because we're interested in an isentropic process, we can set the change in entropy ds equal to 0. Okay, so now we can just rearrange this, so we're getting rid of that term, and it will be integrable. So we're going to divide through by RT to rearrange it. So then we're going to get Cp on R multiplied by dt over T is equal to dp over p. Okay, so that's integrable. So let's integrate it between two states, 1 and 2. So the temperature we're going to integrate between T2 and T1. The pressure will integrate between P1 and P2. And this gives us, so the integrable of 1 over something is just the log of that thing. So we're going to have Cp on R multiplied by the log of T2 minus the log of T1 is equal to the log of P2 minus the log of P1. Okay, now if you recall, the difference between two logs is equal to the log of the ratio of those two quantities. Okay, and also if we have a factor out the front of a logarithm, we can take it inside the logarithm as a power. Okay, so if we do that, we're going to have the log of T2 over T1 to the power of Cp over R is equal to the log of P2 over P1. Now remember, we found some relationships between the specific heats and the gas constant, which I said would be useful. So here we're going to make use of them. So we recall that R is equal to Cp minus Cv, and if we divide through everything by Cv, then we're going to get gamma over gamma minus 1. Okay, so let's use this expression for that ratio, which is the power, and also take the exponential of both sides. Now what we're going to end up with is the pressure ratio across this isentropic process is going to be equal to the temperature ratio, T2 over T1, to the power of gamma over gamma minus 1. So this is the first of our isentropic flow relations, and this is an extremely powerful relation. It tells us if we know how one thermodynamic quantity varies across an isentropic process, we can immediately tell how a second thermodynamic quantity varies. For example, we talked about the flow being stagnated against the front of a Bugatti Veyron. Let's imagine that we have a little pressure tapping on the front of that vehicle, and we measure what the pressure becomes when it's stagnated against the front of the vehicle. Because we know the ambient temperature and pressure, and we know our isentropic flow relations, we'll immediately be able to figure out what the temperature of the flow is as well. So we have the pressure change, or the pressure ratio, in terms of the temperature ratio. But in order to find an expression for the sound speed, we needed the pressure in terms of the density. But it's very easy to convert between the two. We can simply use the ideal gas law to replace the temperatures. So T2 is going to be equal to P2 divided by rho 2R, and the same thing for T1. So the temperature ratio is equal to the pressure ratio times the inverse of the density ratio. We substitute this back into our isentropic flow relation and then rearrange for the pressure ratio, and we get that the pressure ratio, P2 over P1, is equal to the density ratio to the power of gamma. Now if we let state 2 be arbitrary, so we remove that subscript 2, we find that the pressure is going to be equal to a constant, which depends on the initial state, times rho to the gamma. This is that expression that we needed in order to take the derivative of pressure with respect to density and find that final expression for the sound speed. And we're going to do that in the next module.